My name is Lynn Waterhouse, and I will be presenting Improving Age Composition Estimates, Evaluating a Bayesian-like Method for Estimating Ages from Spines with Vascularized Cores. This is work that I did with Guelson da Silva of UFRSA, Lisa Ayoud, formerly of AOTTP and now with NOAA, and John Honig from VIMS. There are a variety of ways that people have used for aging fish. These methods include using tagging, otoliths, jaws, or other bones, a percular series, as well as scales and fin spines. Now, these first four methods are lethal or have a high extractive cost or require a long period of time. The final two, scales and fin spines, are non-lethal, can quickly be done, and they don't affect the market value of the fish, making it an attractive option for using in studies. Today, I'll be focusing on the use of fin spines and rays. Now, there are some problems with using fin spines and rays. Many fish have vascularization that occurs in the core. This includes species like marlin, yellowfin tuna, skipjack tuna, and freshwater species like catfish, brown trout, and white suckers. The zone of vascularization expands with growth, obliterating the rings in the center of the spine as growth continues, obliterating more and more as the fish ages. This is a visual example of the vascularization in a spine, provided by Guelson da Silva. In panel A on the left, you see that vascularization is just in the center, but we can still see some rings. The blue line indicates the total width of the spine. Now in C, for a bigger fish with a bigger spine, the region that was represented by A, shown in blue, has become completely vascularized, meaning all of those rings are now obscured, and you're only left with rings on the outer edge of the spine. People have come up with a variety of ways to deal with vascularization in spines. The naive model assumes that the observed rings represent the true age. People have come up with a variety of other methods, but we will not be going into detail of those methods here, but 4 of them are listed below. We have come up with a new method, a Bayesian-like imputation method, and we will be comparing that to the naive model, which is the most commonly used model, where you assume the observed rings are equal to true age. The Bayesian-like ring imputation for age numbers, or Bryan method, has a goal of estimating the number of missing rings to get the total age, where age equals rings from the inner portion plus rings from the outer portion that you can see. The rings from the inner portion are 0 when there's no obliteration in younger fish, or Na for older fish where vascularization has occurred. The Bryan model assumes that spine width follows a von Bertalanffy curve. There's an asterisk there because you can change that assumption. And the distribution of the rings for the inner portion is assumed to be Poisson with a mean mu sub v, where that's equal to the mean number of rings in the vascularized region for a fish of spine width v. We calculate mu sub v by solving the von Bertalanffy equation for age given vascularization width v. The data required for the Bryan model includes count of observed rings, C sub I, and if rings are missing or not, X sub I. It's going to be Na if some rings could be missing, or 0 if no missing rings. Spine width, D sub I, along with vascularized region width, D1 sub I. And in the Bryan model, your missing rings, X sub I, is distributed Poisson, given by this equation, which represents the age from the vascularized region, where your T0, K, and D infinity are the von Bertalanffy parameters for spine growth. Now, why is it Bayesian-like instead of Bayesian in the name of Bryan? Well, the priors for this model are not purely hierarchical, so it's not strictly a Bayesian model. But these methods that are used for the Bryan model are similar to methods used in data science, where the interest is in prediction, which is the main focus for this model. Today, I'll be comparing the naive model and the Bryan model, using both simulated data sets and yellowfin tuna. The simulated data consists of 1,000 fish, with ages ranging from 1 to 10, with a uniform age distribution. The spine width is based on age following a von Bertalanffy growth model, adding in random error with a standard deviation of 0.1. The vascularized region is proportional to the spine radius, where random error is added in logit space to ensure that the vascularized region does not become larger than the spine radius. And then we calculate the location of each ring, scaling it by the ratio of the spine width to the expected spine width for a fish of that age, with the notion being that small fish are always small and big fish are always big. The next step is to calculate the number of missing rings, and this is done by comparing the vascularized width to the location of each ring. Of course, so we don't actually know this for the observed data portion, we then need to determine if rings are missing, what are the xi's. And this is done by, if we believe we have 1-year-olds in the data set, we can use the smallest first observed ring diameter and compare it to the vascularized region. If the vascularized region is larger, then possibly some rings are missing. If it's smaller, we can set it at 0. It's also okay to assume that all fish are censored and set all of the xi's to NA and treat them as if all could have missing rings. These are some results from the naive method. The rows show true ages, and the columns are the naive age, or how many observed rings we see. Green is where it gets it right, yellow is off by 1, and orange is off by 2. So we see that the naive model does well for really young fish, the 1s and 2s, and it gets it right. But then starting with age 3 and above, the naive estimate starts to underestimate the true age, shown in the yellow and the orange. This shows results from the Bryan model, and we see lots of green, which means it's getting it right. And again, yellow is off by 1 year. A quick summary, the naive model produced a maximum age of 9. The Bryan model produced a maximum age of 11. The truth was 10. The naive model has greater bias in older fish, only does well in young fish. The Bryan model is unbiased and gets it right more than 74% of the time. How do the two models compare in their estimates of parameters from the von Bertalanffy model? For T0, the Bryan model performs well, getting it close to the truth. The naive model overestimates T0, with a 95% credible interval not containing the truth. For D infinity, both the Bryan model and the naive model perform well, estimating close to the true value of 4. However, for K, the Bryan model performs well, estimating close to the truth of 0.4, but the naive model overestimates K at 0.6. Therefore, the naive estimate of K is 50% higher. And if you're using a total mortality estimator, such as the Beverton-Holt mean length estimator shown below, your total mortality estimate will be 50% higher, and this can have drastic consequences for your management. This plot shows curves from the von Bertalanffy parameters for the Bryan model and the naive model compared to the true age data set. So on the x-axis, we have true age, the y-axis is spine width in millimeters. We can see that the Bryan model fits the truth well, going straight through the data. The naive model overestimates the spine width for younger age fish, and again, that's because of that overestimated K. Now switching to our real data example using yellowfin tuna spines. This data set was provided by AOTTP and IFRSA from Guelson da Silva. So our first question is there evidence that vascularization is affecting the apparent growth in yellowfin tuna? So here we have violin plots of the width of the first observed ring in millimeters, grouped by how many rings were counted for those spines. So down here, this is when that spine had 1 ring that was observed, and we can see that the width of that first ring occurs around 2 millimeters. But then by the time we get up here, where those spines have 6 rings that have been observed, the width of that first observed rings is up at 7 millimeters. So this is evidence that vascularization has occurred and that this is in fact not the true first ring, but perhaps the second, third, or something else. We can look at results from applying the two models to the yellowfin tuna data to estimate the von Bertalanffy model. And we see that unlike our simulated data example, now they have very similar estimates of K, but where they differ is T0 and D infinity. In particular, the D infinity from the naive model is much higher at 23.4 compared to 13.3 from the Bryan model. If we want to see how the naive model does with the von Bertalanffy curve for the yellowfin tuna data, we can plot the curve on top of the observed ring count data and fork length data. So the x-axis is observed ring count ranging from 1 to 7, and the y-axis is the fork length. Now, essentially, the naive model fits a straight line through the data, meaning that d infinity and L infinity are quite high, and this is because it hasn't estimated the curvature to be taking place yet. When we then look at how the Bayesian model does, so now we have estimated age from the Bayesian model on the x-axis. So we noticed it runs from 1 all the way up to 14 because we've added in those missing rings. Again, fork length on the y-axis. The Bayesian model fits these estimated ages quite well, and we can see the naive model is shooting off to some very high L infinity. Now that we've shown you how the Bayesian model performs in simulation and with real data, I want to tell you a bit more about the flexibility that this model offers. It can incorporate other growth models instead of the von Bertalanffy if you choose. And from our simulations, we found that the model will still run if 100% of your data has missing rings from vascularization. So if all of those XIs are NA, the model can still perform. And we showed that it did quite well in simulation, as well as performed pretty well for a real-world example, although we don't know how it compared to the truth for yellowfin tuna. Other benefits of using the Bayesian model includes that it allows us to utilize the data in a more efficient manner. We no longer have to do the naive thing and just assume what we see represents the true age. We can also increase our sample size by collecting from catch and release anglers and commercial fishermen, since it's a non-lethal sample and it's fast to take. The Bayesian model also avoids the naive mistake, which in simulations, when you had all ages represented, resulted in us underestimating the age and therefore overestimating K and Z, which, as we mentioned, can have really big implications for your management. This work was funded by the AOTTP Tropical Tuna Age and Growth Study. Data was provided by AOTTP and UFRSA along with ICCAT. We would also like to extend a special acknowledgement to Professor Grace Chu of VIMS, who helped with input on the modeling. With that, I'd like to thank you, and we're happy to take any questions you may have.